In this lesson, we're going to be comparing between Vertex and standard form and also converting between them. So we're going to talk about the characteristics of these different formats, and the first is the leading coefficient A. The sign of A tells us whether the graph opens upward or downward, and then the actual number value of A tells us whether there's a stretch or a shrink. If absolute value of A is greater than 0, there's a stretch, and if the value of A is between 0 and 1, it's a shrink. By looking at the number grouped inside the parentheses with X, we can determine whether the graph has a horizontal shift. It has the opposite sign of what you see. So if you see a minus H in the parentheses, it moves the graph to the right. And if you see a plus H in the parentheses, it moves the graph to the left. Then by adding a number to the end of the equation, this shifts the entire function up or down, and that's a vertical translation. If it's positive, it moves the graph up, and if it's negative, it moves the graph down. We're going to compare this now to standard form and see what we can tell by looking at the equation in standard form. The leading coefficient A tells us the same things. The sign tells us whether the graph opens up or down, and the number value tells us whether there's a stretch or a shrink. At a glance, we can't identify horizontal or vertical shifts by looking at the standard form of a linear equation, but we can identify the y-intercept, and the y-intercept is the point 0c. We can tell whether a function opens up or down by looking at the leading coefficient A. If the value of A is a negative number, then the graph will open downward like a frown. So we're going to identify each of the functions to the left that has a negative leading coefficient. When the equation is written in standard form, we can identify the y-intercept of the function by looking at the value of the constant c, and the point 0c will be our y-intercept. The first equation is in standard form and has a c value of 4, so it has a y-intercept of 4. The second equation is also in standard form, but it has a c value of 5, so its y-intercept is 0, 5 and not 0, 4. The third equation is in vertex form, and we can't determine the y-intercept from this format. The fourth equation is also in standard form with a c value of 4, so we'll check that one as well. Finally, the last equation is in vertex form, and we can't determine the y-intercept from vertex form. To determine whether there's a vertical stretch on our graph, we'll look at the leading coefficient. Remember that we're not looking at the sign. The sign tells us whether there's a reflection, but the absolute value of the leading coefficient A. If the number is greater than 1, it causes the graph to stretch. We're looking for leading coefficients with absolute values greater than 1. Remember, we're not looking at the sign of the number here, just the absolute value. So the first, third, and fifth examples all have coefficients with absolute values greater than 1. It's easy to think that we can tell specific information just by looking at the equation of a function, but we cannot tell the y-intercept of a function by looking at its equation in vertex form. We cannot tell the vertex by simply looking at an equation in standard form, and we cannot determine whether there's a horizontal shift when we look at the equation in standard form. It's important to know the different types of information that we can get from looking at the equation in its different formats so that we can identify the important characteristics of the graph. To convert from vertex to standard form, we're going to apply the order of operations. There's nothing inside the parentheses that we can simplify, so we'll expand out the x plus 1 quantity squared factor. In order to do this, we will apply the FOIL method, or double distributing, in order to simplify the expression x plus 1 times x plus 1. After combining like terms, we'll still have 2 on the outside of our expression, which we will need to distribute, and then we'll bring down the negative 4. As I distribute the 2 to the quantity inside the brackets, that will give me 2x squared plus 4x plus 2 minus 4. Finally, I'll combine the constants at the end of the expression to write the final simplified equation. Y equals 2x squared plus 4x minus 2. Pause the video now while you try these. The last part of the lesson is converting from standard to vertex form. The first thing we're going to do is identify the values for A, B, and C. Then we'll substitute B and A into x equals negative b over 2a, the same equation that we used to find the axis of symmetry and vertex when we were graphing. This will tell us the x-coordinate of our vertex. We'll substitute this back into the original equation to find the y-coordinate of the vertex as well. Vertex form is y equals a times x minus h quantity squared plus k. So we'll take the coordinates of our vertex, negative 2 and negative 3, and we'll substitute those into the equation for h and k. We'll also use the value of our leading coefficient a, which in this function is 1. Substituting these values gives me y equals 1 times the quantity x minus negative 2 squared plus negative 3. Of course, we want to simplify this expression by eliminating double signs, and we also don't need the leading coefficient of 1. The final answer will be y equals x plus 2 quantity squared minus 3. Pause now and try this one on your own. Now you're ready to practice on pages 28 through 30 of your packet. Remember, I'm just an email or a remind message away if you need help.